Alrighty, this is problem set 20, where we're going to start talking about valence bond theory. Question number 1 asks, in 5 sentences or less, describe what valence bond theory is. So just really briefly, valence bond theory is one theory of what bonds are, is a good way to put it. Because we have these molecules, we know that carbon bonds with 4 hydrogens to make methane, right? We know that that happens. The question is why and what actually is that bond, because it's not just a line of 2 electrons that are sitting there in a straight line, right? We know that that's not true. So we're trying to come up with theories that explain why bonds happen and what they are. And so valence bond theory says a bond is equivalent to an overlap in orbitals. I should say in valence orbitals. In other words, we've got C with 4 hydrogens. Valence bond theory says this line right here means that carbon has an orbital that's overlapping with hydrogen's orbital. And that is a bond. We can also use valence bond theory to help describe the geometries in molecules. So we know from valence shell electron pair repulsion, which goes back to my video on problem set 18 about molecular shapes. We know the shapes that exist based off of the steric numbers on the central carbon. So here we would say the steric number around the carbon is 4, and therefore its electron geometry is tetrahedral, and because there's no lone pairs, its molecular geometry is also tetrahedral. So that's valence shell electron pair repulsion, or explains that. But valence bond theory allows us to understand what orbitals might be involved in creating those shapes, which leads to something called hybridization, which maybe we can talk about real quick. So if we look at methane here, CH4, we know that this carbon is making 4 equivalent bonds. Well, if a bond is an overlap in valence orbitals, that means that carbon needs to have 4 equivalent orbitals. Okay, 4 equivalent valence orbitals. But does it? Well, what are the valence orbitals in carbon? S, P, P, and P. So, and then all of these hydrogens are just going to have an s orbital. So we're saying if these were carbon's orbitals, then one of these bonds would be an overlap of an s and an s. Another would be S and P, another S and P, and another S and P. But that would not give us 4 equivalent bonds. So what we end up doing to explain this is we say, all right, carbon needs 1, 2, 3, 4 orbitals, because the steric number is 4. So we're going to take the 4 orbitals it does have. We're going to mix them all up. We're going to take all these guys, mix them all up, and spit out 4 new orbitals. Wow. Called sp3, 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 sp3. In other words, carbon is going to take these 4 orbitals, mix them all up, spit them all out, and we're going to get 4 new orbitals, and this is just the name of the orbital. It's just a name. Don't overthink it. sp3 is the name of the orbital. It's also the name of the hybridization. So here carbon is going to be sp3 hybridized. It's going to have 4 different sp3 orbitals, which then can make 4 equivalent bonds. Okay, we know that an s orbital looks like this and a p orbital looks like this. So if you can imagine hybridizing those, we stick those together, and when we have hybridized orbitals, we draw one small side and one big side. That was not very good. Like that. So this is how we would draw a hybridized orbital. So you can imagine if I were to draw the orbitals on this CH4, we'd have the carbon. It would have 1 sp3 orbital, 2 sp3, 3 sp3, 4 sp3. And then each of my hydrogens around the outsides are going to have an S, an S, an S, an S, and everywhere that you get overlap there, you get a bond. And since all of these are s orbitals overlapping sp3 orbitals, all those bonds are equivalent. Okay, so I could give you could be asked, like, for example, in this molecule, what is the hybridization around that carbon? And you say, well, what's the steric number? 1, 2, 3. That means that I need 3 orbitals, so spp or sp2 is how we would write that. Anyway, so there's just an introduction to hybridization. We're going to use it later on, but it's important to valence bond theory. and it's how we use valence bond theory to explain the shapes we get from the valence shell electron pair repulsion. All right, so let's move on to number 2. Describe the strengths and limitations of valence bond theory with regard to calculating bond energies, calculating bond order, understanding magnetic properties, and predicting molecular geometry. All right, so what is valence bond theory good at? Calculating bond energies. We do not calculate bond energies with valence bond theory. Bond orders, we do. We do calculate bond orders. It gives us a good approximation. In other words, it explains most bond orders very well and some bond orders not so good. But we will learn how to calculate bond order from our valence bond theory. And when we talk about molecular orbital theory, which is problem set 21, which is just a different theory of what bonding is, that gives us kind of a better idea of bond order. But we will calculate bond order from valence bond theory. All right, magnetism. It does not do anything about magnetism. That's like paramagnetic, diamagnetic. We don't do that with valence bond theory. Geometry. I say it gives us the hybridized orbitals. Which then give you the geometry from VSEPR. Valence shell electron pair repulsion. Okay, so for both sigma and pi bonds, describe whether they occur in single, double, or triple bonds. So let's take a minute and let's talk about what sigma and pi bonds are. Okay, so when you hear sigma, what you should think of is between the nuclei. When you think pi, you should think outside of the nuclei. Okay, because in this case we're talking about sigma and pi bonds, but later we'll talk about other sigma and pi stuff, but this is what you should think. Sigma means between the nuclei, pi means outside the nuclei. So a sigma bond, what is a bond? Well, for valence bond theory, a bond is overlapping in orbitals. So in a valence bond, a sigma bond means overlapping of the orbitals between the nuclei. A pi bond means overlapping the orbitals outside the nuclei. So if we were looking at this methane right here, okay, if we were to like draw a line between the two nuclei, that overlap happens on that line. So that would be a sigma overlap or a sigma bond. Okay, let's just talk about what pi bonds would be. Let's say that I had O2. Right, this is what O2 looks like. Okay, if we looked at the hybridization here for each O, 1, 2, 3, steric number of 3, so hybridization is going to be sp2. So each of these oxygens is going to have 3 distinct orbitals called sp2 orbitals. So one's going to go like this, one's up like that, it's down like that. That's that trigonal planar that we get with the steric number of 3. This oxygen can do the same thing. Okay, well, what's this? This is a sigma bond because these two orbitals overlap in between the nuclei. But each of these oxygens started with spp valence orbitals. And they both hybridized 3 of those orbitals to become sp2. So if you notice, each of them still has an additional p orbital. So I'm now going to draw that p orbital. Let's make it green. Okay. Okay, so they still have that p orbital. Now I drew these p orbitals really skinny and I drew these atoms really far apart. But if we were to draw them closer the way it really is, my 2 nuclei, p orbital would look like that and like that. And if you see, what do we get here? We get the overlap of the orbitals, okay, above or outside the nuclei, right? It's not there, it's outside of there. So if we have overlap of orbitals, that's a bond, and it's outside the nuclei, so that's a pi bond. And we know it overlaps in 2 places, but that's really just one pi bond. Okay, so in this O2 molecule, which is a double bond, we know that, has 1 sigma and 1 pi bond. So Here, if we have a single bond, that's always going to be sigma. Okay, the first bond is always sigma. Anything after that is pi. So double bond is 1 sigma and 1 pi, and a triple bond is 1 sigma and 2 pi. All right, for both sigma and pi bonds, describe the region of electron density in the bond. Well, we just said sigma is between the nuclei. The other term that you'll hear is that sigma bonds have electron density on the internuclear axis, meaning the axis, if I were to draw a line between the nuclei, the bond happens on that line that connects the nuclei, or the internuclear axis. And pi happens outside the nuclei. Again, remember those definitions of sigma and pi. In this case, we're talking about bonds, but later we'll talk about other things that are called sigma and pi. And the overlap of orbitals that can produce each bond. Okay, so this is saying, the overlapping orbitals. Well, over here, we showed you this pi bond happened with p orbitals left over. And so pi bonds are made with p orbitals, 2 p orbitals. All right, just say p. But sigma is made with anything anything that can overlap across that line. So that could be an s orbital, it could be an sp, sp2, sp3. Later on we'll talk about sp3d, sp3d2. That's a steric number of 5 and a steric number of 6. And you could also have overlap of p orbitals. So pretty much anything can form a sigma bond. Pi bonds, we typically in Chem 105 say, are just made from p orbitals. All right, determine the number of sigma and pi bonds in the following molecules. All right, this will be fun. So I'm going to use red to mark every sigma. So I'm just going to cross the bond when I count it. So remember, if I have a double bond, that's 1 sigma and 1 pi. Triple, 1 sigma and 2 pi's. So sigmas 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Awesome. So 12 sigma. And I'm going to use purple for pi. 1, 2, 3, 4 pi. That wasn't too bad. Here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma. And pi's 1, 2, 3, 4, 5, 6. 6 pi's. Come over here. Okay, this one's interesting because what haven't they drawn? They haven't drawn all the hydrogens. So if you were to just count the lines drawn, you would get this very wrong. But instead, remember there's a bond between that nitrogen and hydrogen. And then we have hydrogen, hydrogen. That one's good. This has 1. This has 2, 3, 4. So sigmas 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Awesome. 24 sigma. And pi's, see 1 pi. Okay. So just remember, if they don't draw the hydrogens, you've got to. All right, number 5, state the hybridization of the central atom, the molecular shape, and the bond angles for each of the following molecules or ions. And we also want to appropriately state whether bond angles are greater than or less than a specific number. So if we draw the CH3F with my lone pairs. So how do I figure out the hybridization? I just count out the steric number, 1, 2, 3, 4. So I need 4 orbitals. So sp3. That's tetrahedral, both the electron and molecular shape, and bond angles are going to be 109.5 degrees because it's tetrahedral. All right, ClF2 minus. Okay, this is ClF2 minus right there. and steric number 1, 2, 3, 4, 5. So S, P, 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 that's 4, but then we need a fifth. What comes after P's? D's. So sp3d. And so the electron geometry with the steric number 5 is trigonal bipyramidal with 3 lone pairs. It becomes linear with a bond angle of exactly 180 degrees. All right, BRF5. And all these fluorines have lone pairs. Okay, so steric number is 6, so that's going to be sp3d2. That's as high as you're ever going to get, which means that my electron geometry is octahedral, but with 1 lone pair, my molecular shape becomes square pyramidal. And with octahedral, my angles are usually 90 degrees, but that lone pair is going to push everything a little closer together, so my angles are all going to be a little bit less than 90 degrees. All right, and here we're doing the same thing. So SF2. Okay, steric number 4, so it's sp3 hybridized. So that's tetrahedral electron geometry, but they want molecular geometry, so that's going to leave us with bent. And my angles are going to be less than 109.5 degrees. BEF2. Okay, steric number's 2, so it's sp hybridized, which is going to make it linear. So so angles are 180 degrees. And XEF2. Okay, steric number 5, sp3d. This is also linear, which is exactly 180 degrees. And we're just going to keep going doing the same thing. Okay, ClO, move down a little bit. Three minus, so 1, 2, 3, 4, 5, 6. We're going to have that. Oh, I got to start from scratch. How many do I have? 18 plus 7 plus 1 gives me 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So this is a plus 2, so I need 2 bonds. My negative. There we go. And I haven't been drawing resonance structures, but like this one could have a resonance structure. I don't know if any other ones could have. Nope, but this one would have resonance structures, and it's an ion, so I'll just do this. Do that to show that it would have 2 more resonance structures. And it is sp3 hybridized with a steric number of 4. And so the electron geometry is tetrahedral, but then the molecular shape would be trigonal pyramidal. One lone pair, which should make the angles less than 109.5 degrees. BRF3. So we get the electron, or 1, 2, 3, steric number 5. So that is sp3d. Electron geometry is trigonal bipyramidal. Molecular shape, though, is T-shaped with 2 lone pairs. And T-shaped is going to have angles a little bit less than 90 degrees. Carbonate CO3 2 minus. And this is going to have charge of 2 minus, and it's going to have 2 resonance structures, which I won't draw. but we have steric number 3, so it's going to be sp2 hybridized. Now, if you realize sp2 hybridized means that we have an extra p orbital laying around, well, that p orbital is going to participate in the pi bond with oxygen, right? So sp2 hybridized, which is going to make it trigonal planar, and the angles are going to be 120 degrees. All right, state the hybrid. Oh, it's the same thing. I don't know why I keep reading the instructions when they're exactly the same every time. Go. So steric number 6 is going to be sp3d2, which is octahedral electron geometry, but with 2 lone pairs. That becomes square planar, which means the angles are going to be exactly 90 degrees. PF4 minus steric number 5 is going to be sp3d, and that's trigonal bipyramidal electron geometry. 1 lone pair brings that to seesaw. And that gives us angles, so we get a less than 90 degrees. We also get a less than 120 degrees. Because if you remember our seesaw shape, 1 lone pair, these 3 things around the middle are flat all together. They're all coming like in and out of the board. Okay, so from here to here, that's 90 degrees. From this up to this guy around the middle is 90 degrees. But then around the middle, each of these is 120 degrees. So not only does this lone pair push this 90 degrees down by pushing extra on those 2 bonds, but it also pushes our 120 degrees by pushing extra on those 2 bonds. That's why we get less than 90, less than 120. SbCl5. Just make sure Sp has 5 valence electrons, which means with a steric number 5, this is sp3d and has no lone pairs, so both the electron and the molecular geometry are trigonal bipyramidal. And our angles are going to be both 90 degrees and 120 degrees, exactly. All right, good job. Azides are sodium, such as sodium azide, NaN3, are used in automobile airbags as a source of nitrogen gas. Another compound with 3 nitrogen atoms bonded together is N3F. What difference are there between the arrangement of the electrons found around the nitrogen atoms in the azide ion? So the Na is just Na plus that's stuck on an N3 minus, right? So they're just talking about the N3 minus. And in NF3. So is there a difference in the hybridization of the central nitrogen atom? So we're going to draw these. So we're going to have N3 minus, which N has 5, so 15 plus 1 is 16 valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16. Formal charges give me a -2, -2 plus 3. Right, so let's get rid of some. I can get rid of one of those. Bam, now that's a +2. Get rid of one of these. So go, and let's see, this is now +1. Can't do anything else because nitrogen's octet is full, and remember carbon, nitrogen, oxygen, fluorine are the ones that have to follow the octet rule. So I'm done right there, and overall this has an ion charge of -1. And now the N3, that's N3 minus, and then N3F, this is kind of a weird molecule because it actually looks like this. And so when I fill up the valence electrons, let's see, so I'm going to have 15 plus 7 is 22. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, put them here, 20, 22, maybe? We'll see how that works out. So this is a formal charge of -1 plus 3 minus 2. So let's, -1. Let's get rid of this guy first. Minus, bam, plus 2. Then we can get rid of this guy, which do that. That's 0 now, and this is +1. I can't do anything else because the nitrogen's done. Okay, so this is FN3 again, or N3F, weird molecule. What is the difference? What difference are there in the arrangement of the electrons around the nitrogen atoms in an NF3? Is there a difference in the hybridization of the central atom? So this is the central nitrogen. Central nitrogen, what's the hybridization? SP, SP. So there's no difference in terms of the hybridization. Cool. All right, chlorite is used as a bleaching agent. Perchlorate interferes with the uptake of iodine into the thyroid gland and is also used to treat hyperthyroidism, overactive thyroid. Draw the Lewis structure of chlorite and perchlorate, including all resonance structures in which formal charges are closest to 0. Okay, so we're going to have ClO, and this is 7 plus 12 plus 1. Gives me 20 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And formal charge of minus, minus, plus. So let's get rid of one of those. Bam. So here we go. And we're going to have a resonance structure. Just for the sake of being pretty. There we go. Okay. Draw the Lewis structures, including all resonance structures and formal charges are close to 0. Is that all they? Oh, we have more on part B. So let's just draw these first. ClO, 7 plus 24 plus 1. 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Wait. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. These are all minus, 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 and we've got a plus 3 in the middle. So we're going to make 3 bonds. And we're still going to have that minus on this guy. Okay. Overall minus. That means that we have 4 total resonance structures, because that single bond could go on any of the oxygens. Okay, there are all my resonance structures. All right, what is the shape of each of the ions? So this guy has steric number of 4, so its electron geometry is tetrahedral, and with 2 lone pairs, it becomes bent. And then this guy has steric number of 4 with no lone pairs, so the electron geometry and the molecular shape or molecular geometry are tetrahedral. Suggest a hybridization of the central chlorine atom in each of the ions that accounts for its shape. Well, this guy has a steric number of 4, so that's going to be sp3. This has a steric number of 4, so it's also sp3. All right. The C2H5NO molecules below are isomers. The molecule in A is an acetamide, which is sometimes used as a plasticizer or compound added to plastics to alter their fluidity. What type of isomers are these? All right, so what are our options? Just a reminder from the isomer video, which was problem set 19. We could have constitutional, which means that they're connected differently. We could have geometric, which means that they have a switched double bond from cis to trans or trans to cis. And then we could have enantiomers, which means they are mirror images and have a chiral carbon. So here we have carbon with a double bond, or nitrogen to a carbon with a double bond. Here you have carbon to carbon with a double bond to a nitrogen. So those are not connected the same. So these are constitutional. And remember that constitutional is the same as structural. What is the hybridization and the electron geometry of each carbon and nitrogen atom? From left to right. All right, so we've got carbon there, carbon, nitrogen. Remember, this carbon has 3 hydrogens on it. So the hybridization there is sp3, and the shape around that is tetrahedral. This guy, a steric number of 3, so sp2, and that's going to make it trigonal planar. And this nitrogen has 3 bonds and also has a lone pair on it, so that's going to make it sp3. Tetrahedral with 1 lone pair is trigonal pyramidal. That's not how you spell it. Pyramidal. Here we have this nitrogen is the same. This carbon is sp3 tetrahedral. And this carbon is sp2 trigonal planar. Awesome. All right, until the 1960s, all of the noble gases were thought to be totally unreactive. This changed when xenon tetrafluoride was made. Draw xenon tetrafluoride. We end up with 2 extra lone pairs there. Formal charges are all 0. What's the electron geometry? We've got a steric number of 6, so the electron geometry is octahedral. Molecular shape with 2 lone pairs, we're left with square planar. Orbital hybridization, steric number of 6 gives S, so we need 6 orbitals, sp3d2. Based on your knowledge of the atomic electronic structure of xenon fluoride, briefly explain why it is not unreasonable to think that this compound could be made. Well, we know that fluorine really wants an additional electron. And xenon can expand its octet. And xenon is large, so its electrons aren't held super tightly. So they can go out, flirt with the fluorine, and make a bond. All right, so this problem set we talked about valence bond theory. We defined what valence bond theory is. We talked about sigma and pi bonds. We talked about hybridization, and yeah, there we go.